morning, everyone. Welcome to this virtual talk for the MIT Alumni Club of Australia. It's my great pleasure today to introduce Dr. Ryan Anderson, and today he will be presenting a very exciting talk about exploration on Mars titled Have Laser Will Rove. Ryan is currently a senior scientist at the Planetary Science Institute. He has a degree in astrophysics from the University of Michigan and a PhD in astronomy from Cornell University. From 2012 to 2025, he was a scientist at the United States Geologic Survey Astrogeology Science Center, which is located in Arizona. So he's recently changed and started his new role at the Planetary Science Institute. And Ryan has been doing science on Mars for a very long time. He first started working on Mars rover missions in 2007. So without further ado, I'll hand over to Ryan, but it is such a pleasure to have somebody with his expertise talking about this really interesting topic, which for me at least is even more interesting considering the Artemis mission that just concluded and I was watching over the weekend. So I have a renewed interest and excitement in space exploration. Thanks, Ryan. I'll hand over to you. Oh, one moment. For questions, if you have a really pressing question, feel free to raise your hands and I will call on you. Otherwise, remember your question or put it into the chat and we will make sure we save at least 10 minutes at the end so that you can have questions. All right, over to you, Ryan.
Okay, well, thank you very much, and thank you for having me. Today, I'm going to cover a lot of ground. I thought first I would just sort of give an overview of the Curiosity and Perseverance Mars rover missions that are active on the surface right now. I'll highlight some of the results from those missions, and then I'll talk a little bit more in detail about the work that I do, a little more technical detail. And then I'll wrap up with a bit of a plug for some software that I've written that has been helping me out with the work that I do and that I hope will be useful for other people. So a lot of ground to cover. I'll try to move things along so we have some time for questions at the end. So I'll get started here. So first I'll talk about Curiosity, the senior rover on Mars right now. Curiosity landed in 2013. I believe. The primary goal is to determine whether Mars was ever habitable. And so the rover is equipped with a bunch of scientific instruments that I'll talk about on the next slide. But the four main goals are to assess the biological potential of ancient Mars, look at the geology, the geochemistry, particularly the role of water, of course, is important when we're trying to understand habitability. And it also carries an instrument that measures the surface radiation so that when and if we ever do send astronauts to the surface, we know what they'll be in for and how to protect them. So just very briefly, it's the other name for Curiosity is the Mars Science Laboratory, and that's because it carries a whole bunch of instruments, including instruments you would normally think of as laboratory instruments. So the instrument I work on is ChemCam. It's a laser-induced breakdown spectroscopy instrument mounted on the mast with a spectrometer inside the body. There are also color cameras, the mass cams. REMS is a weather station. RAD is that instrument that measures the radiation environment. DAN stands for dynamic albedo of neutrons, is a Russian instrument that allows us to estimate the amount of water underneath the rover. MARDI is a downward-facing camera that was originally designed to be used during landing, but has been sort of hijacked by the scientists since we've landed and is used to take pictures underneath the rover as we drive. And then there's a robotic arm, and on the arm is MOLLE, which is the hand lens camera, the color microscopic imager. APXS is the alpha particle X-ray spectrometer that gives us elemental composition of targets that we can reach out and touch, and a brush and drill and sieves and scoop for taking samples. And those samples are fed to ChemIn, which is an X-ray diffraction instrument, and SAM, which is a gas chromatograph mass spectrometer inside the rover. So with all of that, we have a very capable payload, and we can do a lot of science as we drive around on the surface, and even more once we ingest a sample and analyze it with the lab instruments. So this is a sort of a computer rendering of the rover doing my favorite part of what it does, which is zapping rocks with lasers. So this is the ChemCam instrument. The laser is actually infrared, but that doesn't make for as good of a public relations graphic, so they made it red for that. But this is really how it works. We can zap targets up to about 6 meters away. We really try to aim closer, but it's a standoff instrument that allows us to get an estimate of the elemental composition from a distance. So we zap the rock, get a little spark, and you can see these are real sparks in a laboratory, and you can see the colored emission lines can tell you what the target is. We don't really look at this, we look at this. These are real spectra from the rover of different materials we've encountered. And you can see, even if you don't know anything about atomic emission spectra of major rock forming elements, that these are different, right? This rock has lots of iron and magnesium and manganese. This has tons of calcium and so on. So we can use this instrument to sort of scout ahead of the rover, identify things that are worth the time to go over and analyze with the instruments on the arm. So that's the rover. Now a little bit about the landing site, a crash course in Mars geology here. So the crater where we landed is called Gale crater. This is a grayscale image mosaic from orbit. It's a very large crater. It's about 100 kilometers across. And our landing site was up here in the northwestern crater floor, in between the crater rim, which is this ring of mountains, and this sort of crescent-shaped mountain of layered sediments in the center of the crater. And we went here because it's a nice flat place to land on an alluvial fan, so that's a water-formed feature. And then from there, we drive toward the layers of what we call Mount Sharp. And these layers we knew from orbit before the mission, they have clays and sulfate minerals, and those are minerals that contain water and may contain clues to how Mars's environment may have changed over time, especially in the very ancient periods. So this is how we landed. And I encourage you, this is just a gift to keep things moving in the presentation, but I encourage you to go Google and watch on YouTube the 7 minutes of terror video that NASA made about this insane landing system that we used. It's called the Sky Crane. Basically, the spacecraft came down on a parachute, on a heat shield, and then a parachute, and then it jumped off the parachute onto this hovering jetpack Sky Crane device, I guess. And then as that approached the surface, it hovered over the surface and lowered the rover on a winch so it touched down on the wheels. And then the Sky Crane flew away to crash a safe distance away, leaving the rover on the surface. Amazingly, that all worked just fine. And we landed right here on the plains of Gale Crater. And since then, we've been driving across the plains through these dark sand dunes. Mars is a mostly volcanic planet, so the sand on Mars is dark in color, like the black sand beaches you might see in Hawaii or Iceland. So we've crossed across the crater floor onto the lower foothills of Mount Sharp, and over the last many years, we worked our way up through these layers, and we are now all the way down here. So I'll just go very briefly through some of the cool highlights that we've seen. There's obviously, I could talk for multiple hours about what we've seen, but this is the abridged version so that we can talk about other rovers and other things as well. So our first stop after we landed was this place called Yellowknife Bay. I'll step back one. So it's this sort of contact between three different terrain types that we can see from orbit. And we drove down into Yellowknife Bay and we took our first drill sample, and it was a massive success. We checked off a lot of the things on our to-do list. The rocks here, turns out, are mudstones from an ancient lake bed. The geochemistry of those rocks indicated that the water was pH neutral, so you could drink it and not get sick. It was safe for life. The rocks themselves have chemicals needed for life, including some that are known and used as metabolite that are metabolized by life on Earth sometimes. And there are even some organic, as in carbon-bearing molecules, detected in these rocks. So pretty good first sample for a mission looking for habitability. We found evidence of a habitable lake on Mars. But we had a lot more to do, so we drove from Yellowknife Bay toward Mount Sharp, which you can see here in the distance. Along the way on the crater floor, we came across many instances of conglomerates, where you have lots of pebbles and cobbles that have been cemented together. And so these are the rounded rocks indicate transport by water. We can estimate how much water there was to form these rocks and round them. And then this one in particular was interesting and was a place where ChemCam could shine because we came across this very coarse-grained igneous rock as a clast in the larger conglomerate. And these coarse grains they're too small for APXS to measure individually, but ChemCam's has a sort of a pinpoint laser spot on the target, so we could measure these individual grains and confirm what was pretty obvious to the geologist looking at this rock, that this is plagioclase and pyroxene crystals. This is an igneous rock. And we had never seen an igneous rock like this on Mars before. Everything we had seen was basaltic, meaning it erupted on the surface, cooled quickly, had small crystals. This rock cooled slowly to grow these large crystals, so it must have been intruded underground and cooled underground and then eroded out to form this conglomerate. So that was a cool discovery along the way. As we arrived at the foothills of Mount Sharp, we came across a lot of rocks that look like this, heavily fractured mudstones. And in fact, when we look closely, we could see that there are multiple generations of water. So you have the first generation, the lake that formed the mudstone, the second generation, depositing dark minerals on the outside of these veins, and then the third generation depositing calcium sulfate on the inside of these veins. So complicated story, but the bottom line is that there was water here and it recurred multiple times over a very long time period. Another interesting discovery that ChemCam made along the way is when we stopped at this location called Winjana, it analyzed these targets here, and you can see the laser actually puffs away the dust that are on the surface of the rocks. You get a dark patch where the laser has been hitting. And when we measured these, we got between 5 and 7 weight% manganese in the rocks. That's quite high. Normally, it's more like half a weight% in these sorts of rocks. And so this was a surprise, and it indicates that there was water present and an oxidizing environment present. So it points to a very different environment in ancient Mars when these rocks were being deposited. So we started to climb up the foothills of Mount Sharp, and this is just a photo looking back to our landing site. So this is out on the plains of the crater. These mountains in the background are the crater rim. Yellowknife Bay is right here, and then our traverse is this light line that sort of goes off the left side of the screen. But you can see those dark sand dunes and the buttes and mesas at the foothills of Mount Sharp. And this is taken from Vera Rubin Ridge higher up on Mount Sharp. So from there, we spent a lot of time at Vera Rubin Ridge and studying the clay minerals, and then we continued uphill, sort of down into the right, and this image is uphill. And so we worked our way up through these layers of sulfate-bearing rocks and into this area where there's an ancient, what we believe is a river channel that's been filled in with debris. And we spent some time finding a good place to cross, and then came across here and came across a real surprise. We found these rocks that look like this. They look weird, but it's not clear how weird they are until we actually ran one over with the rover and cracked it open. These rocks are almost pure native sulfur, not sulfate, not calcium sulfate like we were seeing in the veins, but like yellow sulfur. This was totally unexpected. I still haven't heard a very good explanation for this because this is not a volcanic area. But this was another place where, we saw it with the cameras, they look yellow, but ChemCam was also one of the first to flag this and say, holy cow, this is very different from everything else we've been analyzing. Different to the extent that it was so weird we couldn't even quantify the chemistry because it didn't fit with our models. But I remember being on downlink one of the days we got the data, and it just looks totally different from anything else we'd seen. So it was a big surprise. Like I said, I don't have a good explanation for it. The team has come up with a few, but they're all kind of strange. It's a very confusing discovery still a couple of years later. So continuing from there, the last couple of years we've been working our way around this huge butte because up here is all full of sand. We didn't want to get stuck in the sand. So we headed around to the west, and we've been, for the last year or so, been working our way through this area. And this is an area that is full of these resistant ridges that we call boxworks. Usually boxwork refers to pretty small examples of this, but it applies here too. And this is something that in a paper that I wrote in grad school about Gale Crater, we pointed out that there are all these resistant ridges at this sort of all the same level in Mount Sharp. And so we got the opportunity to actually drive the rover there and explore them and take a closer look. This is what they look like from the ground. So you can see in this, this is sort of like a 180-degree panorama, but you can see these large, broad, flat ridges, and then the big butte in the background. Looking up close at the edges of these ridges, you can see these rocks, you can barely even tell what the original rock is. It's so full of nodules and resistant veins and other evidence that water has been percolating through these rocks and depositing minerals and making them resistant. So that's why we have these ridges, is that presumably water was percolating through these large fractures, depositing minerals in the surrounding host rock, and then when erosion took over, these areas were harder, and so they end up being resistant. So from there, this is just a picture that was taken not too long ago, looking uphill at our next target. It's we're basically working our way uphill through the layers of the sulfate-bearing normal layers of Mount Sharp up to this very distinctive light-colored material that we saw way back when we were originally mapping the crater. It's impassable. You can see it's very rough. We're not going to be able to drive over it, but we want to reach out and touch it and get a good look at it, and then we'll probably head to the right and work our way around it to explore other parts of Mount Sharp. And this is a picture from just yesterday. The rover was doing some contact science, brushing these rocks. You can see a brush spot there, taking a close-up photographs of these rocks here before moving on. I don't believe we stopped here and drilled. I think this was just sort of a touch and go. But that's what Curiosity's been up to. So now let's go to the other side of the planet and talk about Perseverance. So Perseverance is the successor to Curiosity, and its mission is similarly, it is sort of four main goals. Looking at the geology, looking at the rock record, looking at the evidence for the past climate, just like Curiosity. But the big difference is Perseverance goes a step further and actually, in its mission statement, says it is searching for evidence of past life, not just habitability. NASA is very careful about how it chooses its words on these sorts of things. So Perseverance is going beyond habitability and looking for past life. And very importantly, is assembling, documenting, and depositing samples to be returned to Earth someday. And also, similar to Curiosity, it had some instruments that were experiments to test and prepare for human exploration. So Perseverance carries an instrument that generates oxygen from carbon dioxide, which astronauts will want to use when we're there. People always wonder what the samples look like. So this is what they look like. They're a little tube, about the size of a test tube, and the drill drills a core into the rock, and what comes out is sort of like the size of a piece of chalk that gets inserted into this tube and then sealed off, and it can be left on the surface or carried in the rover to be retrieved by a future mission. So just like Curiosity, I'll briefly go through the instruments. So ChemCam is upgraded to SuperCam. So it's not just laser-induced breakdown spectroscopy. SuperCam adds infrared spectroscopy, Raman spectroscopy, a color camera instead of a black and white camera, but it still also has the LIBS, which is what I work on. Mastcam Z, again, is an upgrade of the previous cameras. The ones on Perseverance are color, but they zoom. The Curiosity ones, one is zoomed in, one is zoomed out. So Perseverance has color cameras. Its engineering cameras are also in color, which is nice. In place of DAN, we have RIMFAX, which is a ground-penetrating radar. So we can look at bedding underneath the rover, buried underground. MOXIE is the instrument that I mentioned that generates oxygen. And then similar to Curiosity, the robotic arm has a camera, a color camera. Pixel is sort of the next generation of APXS, which instead of just getting the composition of a wide spot, it does a raster of very small spots. And Sherlock is a ultraviolet Raman spectrometer for looking for organics and distinctive minerals in the targets. So I already sort of said this, but SuperCam is the next generation of ChemCam. It adds the IR. Oh, and I forgot to mention, it also adds a microphone. So we're able to do fun things like listen to the sound of our laser spark and use that to estimate the speed of sound on Mars. Fun physics experiments like that. Again, like the other rover, I'll talk a little bit about why we went to this particular spot on Mars. The landing site for Perseverance is Jezero crater. And you can see this is a topographic image. So the red and white are high and blue and purple are low. And you can see that on the western rim of Jezero crater, there's a meandering channel that breaks through the crater rim, deposits this fan of sediment. But the real key here is that there's another breach in the rim on the other side. So this crater didn't just have water flowing into a dry basin. It actually filled up with water and overtopped and spilled out the other side. So we know this was a lake. And this feature here, when we look closer at it, this is an oblique view, it sure as heck looks like a river delta, which is what you get when you have flowing water carrying a lot of sediment that encounters standing water and it drops its sediment, forming this distinctive fan-shaped feature. So this is really exciting because deltas are really great places to trap any organic molecules that happen to be in the water column. Or any little bacteria or whatever's living there gets trapped in that really fine sediment and buried at the foot of the delta. And so that was one of the main goals of the mission, is to check that out. Similar to Curiosity, Perseverance landed with the Sky Crane. The difference is that it had a little bit more advanced computer system, a little bit more ability to steer as it was coming down. So it actually carried a map of the surface made by Astrogeology, where I used to work. And that map was compared in real time with the surface, and the rover could say, oh, I'm about to land in a crater or on a mountain, and divert its path to land somewhere safe, which is why we can land somewhere like this and still feel like we're going to be safe. It knows not to land in this crater or on this cliff. It will land out in this nice flat area. And this time we put more cameras on the rover. So again, I don't have the video just because we're short on time, but I highly encourage you to search for and watch the landing video from Perseverance if you haven't seen it before. These are pictures from the rover and from the sky cranes. So this picture in the upper left, there was a camera on the rover looking up at the sky crane as it was hovering. The sky crane had a camera looking down at the rover as it was descending to the surface. And then the rover had a camera on its belly looking down at the surface, so you can see the sand blowing around as the rockets from the sky crane are disturbing all the dust on the surface. So it's boggles my mind every time I see this picture that we actually were able to land. But it worked. It looks like something out of a 70s sci-fi show, but it really did work. And we touched down right here. This whole area here was marked as impassable, and so as the spacecraft was coming down, it kind of had to choose between this way, and it chose this way. Might have been nicer to land closer to the delta, but we ended up learning a lot landing out here. We did a sort of detour around here to explore this geologic unit and this mostly impassable unit. We did what we called a toe dip into it over here. And then after we were satisfied that we understood those, we sort of hit the road. You can see how far apart these dots are. That means we were driving a lot and not stopping very often. And we headed over to the toe of the delta. So this is what the area that we landed on looked like. We didn't land on areas this rough. It found a nice smooth patch. But after a lot of debate, we determined that this is indeed an igneous composition. It took us a long time to find a rock with these nice textures on it. Most of the rocks look like this. And it's really hard to tell the difference between a sandstone made of basalt and an actual basalt sometimes. And so we did eventually find these rocks, and the distinctive texture here indicates this is a primary lava flow. And this is what our first spectrum from SuperCam looked like. This is the press release figure that I made for our very first spectrum. We landed in an area um, where all the names were based on the Navajo Nation, which is nearby me here in Flagstaff, Arizona. And so all of the targets in the first part of the mission have Diné names. We worked with the Navajo Nation to come up with a list of names. And our very first target is named Maz, which means Mars. And this is about as textbook a basalt as you could imagine. It has all the main things that you would expect to see in a basaltic rock. From there, we did our little toe dip into Ceata. This is also igneous, but it's very, very high in olivine. A lot more magnesium in these rocks than the Maz Formation. From there, we drove around toward the delta, and we got our first good views of this little remnant that we call Kodiak. And this is the telescope view from SuperCam, getting a little bit higher resolution. And again, sort of textbook example of a delta where you have these tilting beds. These are the four set beds of the delta, and then these horizontal beds down at the bottom. That's where all the good stuff is. That's where we want to drill and get samples that may trap organics. So zooming out on our whole traverse now. So we landed over here, drove down here, came around. This butte here is that Kodiak butte. And then we spent a good amount of time here at the toe of the delta collecting samples and examining those bottom set beds. And then we sort of sped up and tried to get across the delta and up into the crater rim to some of the more ancient rocks. On the way across the delta, we came across these. These were seen from orbit, and this is some of the best evidence that this fan was formed by flowing water. These are diagnostic sort of curved deposits that you get when you have a river channel meandering back and forth. And it deposits and then it erodes into its own deposits, and you get these sort of swooping, self-truncating layers. So we spent some time crossing these. We took a sample here. This is what they look like from the surface. I always think it's cool to see the orbital picture and then the surface picture side by side. So you can sort of match up what you're seeing from space with the closest thing we have to an in-person view. From the delta itself, we crossed over to this more rubbly material and into the sort of the channel that fed the delta. And some of you may have heard we brought a little helicopter along with us, our own little drone. It was mostly a technology demo to show that yes, we can make a helicopter fly in the very, very thin atmosphere on Mars. But our little Ingenuity helicopter finally met its fate here in this dune field. It had a camera looking down that it used both to take pictures and to navigate and tell which way was up. And that process of telling which way is up relied on seeing some landmarks in the picture it was taking. And it flew over a patch of sand dunes that was too smooth. And it lost track of which way was up. And it had a hard landing where its rotor actually touched the ground and broke off the tip of one of the propeller rotors. And so it didn't die. It was still functioning, but it couldn't lift off again. So we had to leave it there in the sand. But the other reason to show a zoom in here is because probably our biggest discovery of the mission to date is when we drove over here onto the small patch of bright material that's sort of underneath this crumbly unit that we were exploring. We had seen this early on. I and others had seen this when we were mapping the landing site before landing, and this was marked as an area of high interest. And so we finally got there, and we found this. This Chavaya Falls target, found a couple years ago, and it has olivine grains. You can see the distinctive green crystals. It has calcium sulfate veins. Those are not really, headline-making discoveries. The headlines come from these little leopard spots. These are little spots in this otherwise sort of red-looking rock where the iron has been reduced, and so it's no longer red, and it's been redeposited as these dark rings, irregular rings. Looking at these with pixel, we can see that those rings have iron and phosphorus in them. And Sherlock's Raman spectrometer detects organics in this rock. And on Earth, when you see these reduction spots, the most likely culprit is bacteria. That doesn't mean that this rock has bacteria in it. It just means that if it doesn't have bacteria, it must have something else that's doing the same job that bacteria do on Earth. and we can't really tell what that would be unless we bring the sample back to Earth and analyze it in the lab. So it's a very exciting sample. It may be evidence of bacteria or something similar on Mars, or it may be a different chemical reaction that in the absence of life proceeded and did the same thing. But we really need to take a closer look in a laboratory on Earth to tell the answer. So we took a sample. So this is what that outcrop looks like in context. We like to take selfies with the camera on the robotic arm every time we drill into a rock, both for press releases and for documentation of the rock. So you can see we abraded the rock, we ground off some of it, and then we drilled a hole here. And here's the rock. And then this is the sample itself. This is looking down into the drill bit, and we can see the sample of rock in there. And if you squint, you can see there are actual little leopard spots in there. So we got them. We just have to bring them home. So from there, we have been working our way out of the crater. The delta was one of the major reasons we went here, but the other reason, and we actually almost ended up choosing to land outside the crater first and driving toward the fan. But the rocks outside the crater are very, very ancient, and there's a lot of evidence for water and alteration in these rocks as well. And so we're kind of getting the best of both worlds now. We got the delta, we took samples along there, we got Archivaya Falls, leopard spots here, and now we're driving up onto these very ancient rocks outside the crater, and we are actually somewhere over here as of today. I'm a sucker for a pretty picture. This is a view from right here on the traverse, looking down along the crater rim and just looking at the hills in the distance as we traverse across it. And then this is our latest sort of nice, pretty panorama from a week or so ago, looking at some of these dunes over here. But we're working our way across here. I'm not sure where our next major target is out here. You know, the story was easy when it was drive to the Delta. Now it's in a much more complicated terrain. So we're just working our way along and heading to interesting outcrops that the experts in this area think will tell us more about ancient Mars. Okay, so that's the rover update part of the talk. Now I'm going to very briefly go through a little bit more technical stuff about what I do on the LIBS quantification. So hold on. If it's interesting, I'm glad, and if it's not interesting, it won't last long. So we'll just move through it fairly quickly. So quantification with LIBS is very difficult. We zap the rock, we get this laser plasma, but it's not in thermodynamic equilibrium. It's a very, very rapidly changing plasma, and we integrate over its entire lifetime just due to the limitations of the way the instruments are designed. So it's really hard to do a first principles like physics-based quantification. So instead what we do is we sort of brute force it. We shoot a bunch of different materials in the lab where we know their composition and we can get their LIBS spectrum. And then we feed those into machine learning regression models to come up with a sort of a statistical correlation to estimate what the composition of an unknown spectrum is. So it's a regression problem. We have a bunch of X variables, that's our spectrum, and we're trying to predict a Y variable. That's one of the major rock forming elements. We do this by shooting samples in the lab, and we assess how our models are doing by looking at the root mean squared error. You might think, why don't you just take, if you're trying to predict the amount of sodium in the sample, why don't you just look at the sodium line? I wish it was that easy. My life would be a lot easier. But unfortunately, in the plasma, there are a lot of interactions between elements. The abundance of one element can affect the emission strength of another element. And so collectively, we call this matrix effects. Basically, things that make your life less simple. And so you can't rely on just the information from the element you're trying to predict. You also have to fold in the effects of these other elements. And so we take the whole spectrum or many sections of the spectrum and feed them into these regression algorithms. Again, you might say, well, why don't you just do, your favorite algorithm and do regression with that? No such luck. There's no single algorithm that we've found that always is the best. Just the different properties of these different algorithms, might do fine on silicon, but poorly on potassium. And it's just sort of a kitchen sink approach where we try everything we can and see what works the best empirically. And then we use those to make our predictions. To optimize these models, they have multiple parameters. And as any good first-year student knows, when you have a polynomial, you don't want your polynomial arbitrarily complicated because it'll fit all your data, but then be terrible when you predict something new. Same thing applies for these multivariate regression models. This is an example of cross-validation for a partial least squares model. But basically, the x-axis is the complexity of the model. And as you can see, the red curve is how well it does in predicting the data it was trained on. And that will arbitrarily get better and better and better as the model gets more complex. The blue curve is how well it does on data that has been held out from creating the model, the cross-validation data. And you can see it flattens out, which means you don't want a model that uses 20 components. You probably want to stop at about 9 or 10. Same concept applies to all of these different methods. So we use a cross-validation method to sort of find that sweet spot where it's complex enough to do the best that we can without overfitting, without ending up in a situation like a arbitrarily complex polynomial. We also do tricks like blending submodels. We found that asking a single regression model to be able to handle everything from something with no silicon at all to nearly 100% silicon, it's too much variation in the spectrum. It's too different for a single model to handle very well. And so we train specialist models. So you might have a model specializing in the low end and a model in the high end, and then an overall model. And you can use a combination of those to get a better result than you would from any individual model. So right now, for the past few years, we've been working on an updated calibration using a new spectral database. It significantly increases the number of targets and the number of spectra, particularly trying to fill out some of these high ranges where we had very sparse distribution of samples before, because all these models that we're using are pretty good at interpolating between samples they've seen before, but they are either terrible or incapable of extrapolating beyond what they've seen before. So we want to make sure our lab data spans everything we could possibly expect to see on Mars. So that's why increasing the size of the database is a really good way to improve our prediction results. So the big effort for this new calibration is we've basically been rewriting the pipeline code, leveraging a lot of code from previous work, and this tool that I'll talk about in a couple slides. We've moved a lot of the cross-validation to the cloud because it's time-consuming, and I didn't want my computer melting. And a big part of this is we've taken pre-processing steps, like how do we normalize the spectrum? How do we choose which parts of the spectrum to use? Those were previously being sort of tuned outside of the optimization process, but we realized like really those are extra parameters of the model, even though they're not inherent to the actual regression. So we kind of folded those all together and are now tuning those as part of cross-validation. So we hope that will allow us to get better pre-processing and better results from the models. And this is what our results look like. This is sort of our 6-plot summary of how we're doing on any given element. And basically a good model would fall on the 1-to-1 line in these 4 plots here. And these are looking at the test set. This is data that the model has never seen before. Shifting the spectrum a little bit in case the wavelength calibration gets off, looking at the calibration targets that we carry on the rover, and also looking at, are we varying smoothly between shots of the laser as we analyze samples? Because in previous models, we've seen anomalous behavior where it would jump between 2 extreme results between individual laser shots. So all of this together lets us choose models that look like they're doing pretty well. And we're on the final steps right now of validation, trying to make sure that the models that we think look good are actually giving us geologically reasonable results. So we're looking for spectra where we have outside information from either other spectrometers on SuperCam or other instruments on the rover, where we're pretty sure we know what mineral is there, and then make sure our models are giving the right answer. So there's a lot of iteration, a lot of work with the geochemists on the team to make sure that the responses from the models are as accurate as possible. But we're very close to the finish line on this. So probably in the next 6 months, we'll be able to publish this updated calibration. And then very quickly, and then I'll leave time for questions. I wanted to plug this software that I wrote. This sort of came about after we did the first round of calibration for SuperCam and ChemCam. Basically, I wrote the tool that I wish I had had when we started. This is an open source tool that allows scientists to do a bunch of spectral pre-processing, avoid reinventing the wheel, and just focus on doing science. It's all written in Python. And it has a graphical interface. If you're not a command line programmer and you still want to do this sort of thing, we have a GUI that you can use. I won't go through all the bullet points here, but it does a lot of pre-processing, data transformation sort of things. You can remove continua. You can transform spectra from one instrument to be consistent with spectra from another instrument. You can do a bunch of manipulation and visualization, simple stuff like principal components, complicated stuff like TSNE, clustering, and member identification on mixing, and of course regression, because that's my bread and butter. That's what we do a lot of. So many of the algorithms that we use for SuperCam and ChemCam are available in PyHat to be used with any data set that you want. And finally, just last year, we had a little bit of funding from USGS to write the capability to read in hyperspectral image cubes like the ones shown here and do band math on them. So you can make simple band parameter maps, minimal proxies for minerals in these maps of the surface. And the output can be written back to a PNG or a GeoTIFF that preserves all the geographic information of the original cube. So we hope that'll be useful for people. So if you want the code, this is how you get it. If you're interested, if it sounds cool, but you're not sure what you could do with it, just let me know. This is my email address. I'd be happy to chat by email or set up a call sometime. So that is where I'll leave it. I know that was a lot, but I think we have a little bit of time for questions about any of the various things that I've covered.
Thanks, Ryan. That was a great talk. So we have about 15 minutes for questions. If anybody has a question, feel free to unmute yourself and ask it or raise your hand. I see JB there has a question. Go for it.
Yeah, hey, how are you doing? And thank you very much for such a great presentation. Just a
Thank
quick
you.
question. It's fascinating for me that you're still improving the model on a device that was designed and built years ago and sent there. So it must have been that the model was considered good enough to actually send the module then. But then years after years, you've improved it. How much better is it now compared to when it was when you sent it?
So a confession and a revelation about space exploration is that we didn't have a model when we launched. We basically there was not enough time or funding to collect the data and do all of the work involved in producing that model before launch. So the idea was we built the instrument, and you always build a copy of the instrument to keep in the lab at home. And so the plan from day one, this wasn't like a change of plans partway through, is that we launched the flight instrument, and then back home we shot all of these lab samples with the lab instrument, and we build the model based on that over the first during the flight to Mars and over the first year or so of operations. We sort of developed the initial model, and then once that came out, it came out because we knew we needed something, but we all already knew there were shortcomings. For example, I don't think I'm giving any secrets away when I say that our titanium model it just is incapable of predicting high titanium because the training data we had only went up to about 3 weight percent. So if we shoot a mineral that has 50 weight percent titanium, it'll say 3. And we know that was a known limitation, but we had to get something. So we got our initial model out, but now we're trying to sort of polish it and get the definitive model that has that greater range and has some of the lessons learned from the previous models. So yeah, believe it or not, we launched with no model at all. And you can do a lot even without the quantification with these instruments with LIBS, because a lot of the value of LIBS is just novelty detection, is saying that spectrum is very different from all the other spectra we've seen. So let's go look at that more carefully. So in that regard, we were able to do a lot of useful science even without the numbers, but it's nice to get accurate numbers now.
That's really interesting, Ryan. David, you were next to have your hand up. Please ask your question.
Yeah, hello. Am I coming through okay?
Yes, we can hear you.
Yes.
Okay. Very impressive, Ryan. All that data crunching makes me wonder about the archiving of the data, in particular, the raw numbers that come first off from the instruments. What are the arrangements for archiving that?
Yeah, so all data from NASA instruments is archived on a system called the Planetary Data System, or PDS. And so if you just Google NASA PDS SuperCam or ChemCam, you'll find the website, and the raw data is available there with information on how to read it and how to work with it. So yeah, NASA does a pretty good job of archiving things. I think there's about a 6-month delay from the live data to when it actually gets archived. Raw images are published on the NASA website right away, but more complicated data products like spectra, they go through that 6-month wait before they're officially archived.
Interesting, Ryan. Just a quick follow-up question to that, and then we'll get to Jyoti's question. So I know from working on rocks on Earth that sometimes you zap a rock or you do something and you just get a bad result for whatever reason.
Yep.
With that data all being public, do you sort of flag when maybe something hasn't been quite right, there's been too much dust on the sample, or how do you take that into consideration?
Yeah, we have members of the team who go through and either remove the really bad data. Like sometimes we'll just not be in focus and the laser won't make a spark.
Exactly.
And so
Yeah.
we just get noise. So those are removed. Other ones are flagged. Either, for example, our current quantification, we know there's an issue on some of these really high magnesium rocks where if you add up all of the major elements, you get over 100%, like way more than 100%, like 120. We know that's a problem, but it's our best calibration so far. And so those, I believe, are published but flagged as, there might be something weird going on here, but here's what we have. And the spectrum is there. The spectrum is still good, but maybe maybe the amount of iron predicted is off. So those results are present, but we try to warn people when there might be something up, whether it's focus or other effects. If we think the spectrum is usable, we'll still publish it, but we'll put some warnings on it.
Excellent. Jyoti, you've got a question. Please ask your question.
Yes, thanks for the really good talk. I know with LIBS you ablate material. So do you pulse the laser so you can see kind of at different depths how composition's changing or how the dust is different in the different locations?
Yes. So this here is actually a surface target called Natani. This is a case where we did it was called depth profile. Normally, when we do an observation, we shoot it 30 times per location. But every once in a while, when we think there might be evidence of a coating or something on the rock, we'll do a depth profile. So this was 150 laser shots on the same spot. And you can see this is a magnesium model result. So you can see the magnesium increases for the first 20 shots or so, and then it drops off as you get deeper into the target. It's not a really deep hole. It's still, less, maybe a millimeter at most, but you can get this sort of profile on some of the targets, and on some of the pictures that I showed from Curiosity, you can actually see where we ablate away or clear away the dust on the target, like these ones. You can see the laser spots. They're tiny, but we do drill it in, and we can detect thin coatings like that.
That's neat, Ryan. So I'm really curious. You mentioned it and you said there wasn't a good explanation. What are a couple of the ideas for those really weird sulfur rocks? Because I don't have a good thought about that.
Yeah. So I'm going to butcher this because I'm not a geochemist. I'm barely a geologist. Um, I gave it this similar talk a few weeks ago as a colloquium talk, and I was looking it up to see if I could share the explanation. And the best explanation I found in the literature is something involving clathrates, which is when you have ice that traps other materials in the
Methane
ice.
classes. Yeah.
Yeah, so if you had a sulfur clathrate of ice,
Hmm.
somehow, but I don't understand that mechanism. It's such a strange, it's not a familiar thing. On Earth, you
Hmm.
think you see sulfur, it must be a volcano, right?
Hmm.
So the APXS team came up with this idea where you can somehow concentrate sulfur in a clathrate, and then as the water sublimates away, you can concentrate it down into these deposits.
Hmm.
That's the best explanation I can give you. I I probably didn't do it justice, but that's the best I've
I'll
heard.
read about it, but yeah, that's such a weird rock, Ryan.
Yeah.
Really, really fascinating. And
And this
isn't it
wasn't
nice
just a
that you get these
one-off. We saw
surprises?
many of these.
Wow,
Yeah,
fascinating.
there was tons of these.
Are there any other questions?
Yes, I do have one.
Go ahead.
Thanks for the presentation. It was like really good. I'm just
Thank
thinking,
you.
like a couple of points. First is how regularly do we collect the soil or rock data? Just thinking about the perspective of the soil testing for farming from the Earth. Yeah, and also the technologies used, the camera, sensors, sound. Is there any like industry application like at a affordable way for small and medium companies?
Okay, so the first question was how often do we collect soil samples in particular? Um, I don't have a exact answer, but I know we've collected a few along the way. Usually it's when we encounter a sand dune of interest. If I went back to the Curiosity, when we crossed those black sand dunes, we collected some of that. Um, but it's not super often. It's not like we're taking a regular sample along the way because our sampling capabilities are limited, especially on Perseverance. We only have 42 sample containers total.
Mm.
So we have to be very, very careful about which ones we sampled. And all the samples that we took on the crater floor, we actually took two samples because we deposited some here as a sort of insurance policy in case the rover dies, and we carried the rest with us and collected the remaining samples. So I think we probably have two soil samples in Perseverance right now.
Okay.
And Curiosity, we can reuse the sampling cells, but they get contaminated. So it's not as clean a measurement after the first one. So we do soils occasionally, but it's mostly drill finds.
Yeah.
And then your second question, can you repeat that? It was
Oh, the
about
second
applications.
about the technologies used, the cameras, sensors, laser, and the sound mic. Is there any like an industry use at an affordable way? Because obviously this will be more expensive for the mass.
Yeah.
Yeah. So yeah.
Yeah, a lot of these instruments are used in various ways in industry. Color cameras are nothing special, so there's plenty of instances where you can do that. But some of the more exotic instruments are also used. So the ChemIn instrument on Curiosity is a portable X-ray diffraction instrument, and I know they have a version of it that can fit inside a sort of a briefcase, and you can take it into the field and either do geology, or I know they have also used it in sort of field service work for things like identifying counterfeit drugs, because you can do X-ray diffraction on medicine and tell what the ingredients are. So I know that exists. LIBS is used in industry quite a lot. A lot of the literature is industry, and they have a much easier job because if you work at a steel mill, you know you're shooting steel, and you just need to figure out the variations in its composition. Whereas Mars gives us a wild card, and we need to predict anything that Mars throws at us. But yeah, there's a lot of industrial applications for LIBS because you can analyze a target from a distance without touching it. So the reason that these instruments were made at Los Alamos in the first place is because Los Alamos was interested in them for analyzing nuclear isotopes that you really don't want to touch, but you can shoot through a window and analyze them from a distance and tell something about them. So there's, the people on our team don't do that, but they have colleagues who do. So there are many applications, and I'm sure some of the other instruments, the Raman instruments, there are lab Raman uh, spectrometers that are much more sensitive and work better than the portable ones that we have. Ours tend to be a little bit noisy because you can't prepare the sample as cleanly as you could in the lab on Earth.
Fascinating, Ryan. The last question I have is there a concrete plan for retrieving their samples? I know right now funding and such at NASA is changing, but what was the time frame for those? How long could they stay before you would need to collect them?
Yeah, so that is the big question, right? Um, we launched and we proceeded with the mission being told that there would be a sample return mission that would come and pick them up. Uh, as of last year, that mission has been canceled.
Okay.
It was in funding trouble, and the new administration was looking to cut funding wherever possible, so it was cut. Um, that said, we do still have samples on the surface at our cache here. We're still carrying and collecting samples in the rover, anticipating that eventually there will be an effort to return them. We don't know what that will look like. We don't know if it will be led by NASA or ESA or some combination. It was supposed to be a combination, but NASA lost its funding for that. So it's very much up in the air right now. We don't really know what will happen, but it would be a shame to do all this work and not return the samples. So we'll see. The samples are designed to be stable on the surface of Mars for decades.
Okay.
We take very careful documentation of the ones that we drop on the surface so that we can find them again, because over many years they'll be covered in dust and blend in like chameleons. But we know exactly where they are. The plan before sample return was canceled was because the rover is still healthy, the idea was that the rover would hand deliver them to whatever vehicle lands and is going to return them to Earth. So if that's the case, then it's much easier because you don't have to do a scavenger hunt to try to find your samples. You can just hand them over. So we'll see. A lot of things are up in the air right now. It's a very uncertain time for space exploration, but we're continuing to do the best we can and collect the best samples we can. And we hope that someday they get back to Earth so we can look at them with all the latest and greatest laboratory instruments.
Thanks very much, Ryan. I think that's a good place to leave the talk. We're at time. Really appreciate it. This talk is recorded and will be up on the MIT YouTube page in the next week or so if you want to share it with anyone else. I think this was an absolutely stunning talk. So thank you so much, Ryan, for your time
Thank you.
and sharing your expertise and experience.
Yeah, it's been my pleasure.
Have a great day, everyone. We'll see you at the next talk.
Bye, everyone.